In this section, we'll continue our investigation of the flow phenomena that occur in scramjets. This section is on shockwaves. Shockwaves were briefly introduced in section 1 of the course, but now we're going to look at shockwaves in much more detail. We'll investigate how we can go about calculating what changes occur in the flow properties of a gas after it has passed through a shockwave. So let's go back to our simple scramjet configuration. Vince took you through the type of flow that occurs in the nozzle of our scramjet design, isentropic flow. Let's now move up to the front of the engine, the inlet. As I introduced in the last unit of the introductory section of the course, the type of inlet we have used for our scramjet design is called a mixed external and internal compression system, and this design is shown in Heiser and Pratt's book. The compression of the flow coming into the engine is done through a series of 3 shockwaves. As the flow enters the engine, the top surface of the engine is at an angle to the oncoming flow. So the flow has to deflect. The thing that does the deflection of the flow is an oblique shockwave, indicated here by a dashed straight line. One of the features of shockwaves in a two-dimensional inviscid flow is that the flow downstream of the shockwave all ends up travelling parallel to the surface that caused the flow deflection. Let's zoom in on that first part of the surface of the inlet and the shockwave it generates. Now let's put some lines in the flow to show where the flow are going. These are streamlines in the flow, and they show the direction of the flow. There's no flow across streamlines, so all the gas initially between consecutive streamlines stays between the streamlines. These streamlines show that the flow upstream of the shockwave is all travelling horizontally here. But behind the first oblique shockwave, the flow is all travelling parallel to the surface that caused the deflection. Let's look back at our inlet. There's a second deflection of the surface of the inlet that occurs about halfway along the body of the inlet. This surface deflects the flow even more, and this generates our second inlet shockwave. Let's see what this does to the flow. Again, the flow wants to travel parallel to the surface that caused the deflection. So behind the second shockwave, the flow is deflected downwards further. Let's again look back at our inlet. The cowl of the scramjet, the lower surface in the schematic shown here, generates the third shockwave. The inner surface of the cowl is aligned so that it is parallel with the flow coming onto the scramjet upstream of the inlet. This final shockwave turns the flow so that it is parallel to the cowl's inner surface. Where this third shockwave strikes the upper surface of the scramjet body, the body has one final kink in it, and the shockwave cancels at this point. So what we have coming out of the inlet is a uniform flow that's all travelling parallel to the walls of the combustor. So let's look at what the inlet has done in this case. The inlet has taken the oncoming flow and forced it to pass through a smaller area. We saw in the section on isentropic flow that if we reduce the area for a supersonic stream of gas, we increase the pressure and temperature and decrease the Mach number. Now the flow through this inlet is not isentropic, but this processing of the air through the shockwaves in the inlet does increase the pressure and temperature and reduce the Mach number. We'll find out that the flow does not remain at constant entropy when it passes through a shockwave. Therefore, we can't use all the analysis we've covered in the section on isentropic flow. So we need to find out a little more about shockwaves so that we can calculate the flow properties coming out of the inlet. I should point out that we've chosen all straight surfaces for our inlet. This results in shockwaves that are all straight and the streamlines in the different parts of the inlet that are straight and parallel. This is a good scramjet inlet to keep our analysis tractable, but may not be the best for scramjet inlet design. Note that all the shock waves in the inlet for our scramjet are inclined at an oblique angle to the oncoming flow. As you may have noticed, I referred to these as oblique shock waves. The flow deflects as it passes through the shock wave, as shown here. Another important class of shock waves are referred to as normal shock waves. A normal shock wave forms at an angle of 90 degrees to the oncoming flow, as indicated here. Again, the shock wave is indicated by the dashed line. The flow does not deflect as it passes through the shock wave, but its properties, such as pressure, temperature, and Mach number, do change. In fact, the flow goes from being supersonic upstream of the shock wave, that is a Mach number greater than 1, to subsonic after the shock wave, a Mach number that's less than 1. We can also get shock waves that are curved. In this diagram, I show a uniform flow encountering a shock wave that's curved. Behind the shock wave, the flow is deflected and the flow conditions change. As indicated here, a curved shock wave usually leads to a non-uniform flow downstream of the shock. So the flow direction and flow speed and the pressure and temperature may be different for different streamlines passing through the shock wave. In this section of the course, we'll concentrate primarily on normal and oblique shock waves. We'll analyse the flow through normal shock waves before we tackle oblique shock waves in the upcoming units.